have 3 meter and 4 meter in X and Y directions, respectively. And for the end node, which is node 3, you have 6 meter and 0, respectively, in terms of X and Y. So these are the coordination systems for the start and end, and you can calculate CNS based on these data. See here, we are just starting how we calculate CNS uh, for in the Excel in a way that, for example, see here, if you forget about this number, I just delete it. You can go and click here. You can see this line here. You can say equal sign, bracket. You can click here. This is xj minus xi, close the bracket, divide by lengths, and press enter. When you do this, if you click again on this cell, you can see the formula here. The formula says J2 means this cell, J2. Okay? The columns are named A, B, C, D. The rows are named 1, 2, 3, 4, right? So J2 means this cell. It's the column J, the row 2. All right? H2 means this cell. All right? G2 means this cell. Basically, it means that I'm calculating xj minus xi over L, which should be the formula to calculate C, isn't it? But the power of the Excel is when I write this formula here once, if I grab this point, you can see my mouse cursor, don't you? See my mouse cursor, this is just a picture. Don't worry about this. You can import any picture from any JPG file or other sort of files into this sheet. That's fine. You can make it smaller, bigger, whatever you want. The numbers are in the cells. All right. You can see my mouse cursor, and if you go and click here, if you go here, you can see the mouse cursor shape is different. It's like a plus sign, right? It's not here. It's a big plus, but it's a small plus here. When it's a small plus, if you grab it and bring it down, what happens is this formula will be extended to the other rows in that particular column. It means that when this is J2 minus H2 over G2, the next one will be J3 minus H3 over G3. It means that the C formula is working for the element number 2 as well. It means that you need to write the formula once and just grab it and bring it down, and it will be copied in a way that all the formulas will be calculated for all your elements. These are errors because we don't have any data here, so I just simply delete these. So this is the way we work with Excel, and Excel, any sort of formula you have, you need to write it once and just copy it for all other cases you have, and it makes your life very easier when you have a very big structure. So I can have, besides, I can have more sheets, several sheets. For example, here I have this info sheet, then K1, K2, K total again, boundary, solve. You can see I have different sheets at the bottom, and you can create new sheets like here, new sheet. You can create new sheet, for example, here. It's a just blank sheet. You can do whatever you want to do. I just delete it. And that's why I'm using different sort of sheets to have different concepts in separate sheets. So the first sheet, which is information sheet, I try to have the information for all the elements, the elements characteristics. And then in the K1, I'm trying to assemble the stiffness matrix for element number 1. All right. So for this purpose, you need to use this formula. This is our topic last week. This is the stiffness matrix for a particular element when you have a frame structure. All right. And how many parameters do you need for assembling this? Obviously, you need A, you need I, you need, let's just start from here. You need E, you need L, you need A, you need I, and you need C and S. So 6 parameters are players in this matrix. E, L, A, I, C, S. So I need to have these 6 parameters for a particular element. All right, to be able to assemble this matrix. Do I have them? Yes, I do, because these are 4 of them and these are the 2 rest of them. These yellow ones are those 6 parameters which are listed in the info sheet for every single element. For example, for element number 1, I need these 4 numbers and these 2, altogether 6 numbers. So I need these 6 numbers to be used here in K1. Okay. I just put the formula here just to be just to have everything beside me, and I just bring them. These are the 6 parameters: E, A, I, L, C, S. Okay. To repeat them again, to have them in this sheet as well. See, I put E. It's just a character. It's not something special. It's just a character E. In this one, I just delete it. See, my stiffness matrix depends on this, and if I delete it, everything will be 0. But I want to show you that when I write E here, I can go to this cell and I can say equal. You can see equal here. All right. I click on info. I click on E for element number 1 and I press enter. All right. You will have this number is coming from here. So see this number is equal to info, which means info spreadsheet D2, the cell D2. In the info, D2 is here. See, D2. So basically, I'm connecting this cell to the previous spreadsheet cell, and I have the E here. So for example, if you go here and change this one to 10, you will see it's updated to 10. It means that this cell is connected to that cell in info spreadsheet. Whatever you put here, the K1 will be updated. So it means that, for example, if you do the whole analysis for this structure, and at the end of the day, for whatever reason, you want to change something, if you change something here, all your calculation will be updated. You don't need to go again over the other formulas to update them. It means that all the formulas together are connected, linked together, and they if you just change the information here, all the corresponding other spreadsheets will be updated based on whatever you put here. All right. So I just go to the initial 70 gigapascal and come back here. Okay, I linked all of these to the previous sheet info sheet. And based on these 6 parameters, I want to assemble this matrix, which is the stiffness matrix for element number 1. All right. And I need to follow this formula here. For example, for the first, I need to write it once and I have to do it. And then I can copy it for the other elements like element number 2. But for the first one, I need to write this formula. Can you see it here? In the cell number 1 and 1. I need to write, but keep in your mind, you have E over L as well. E over L times AC2 plus 12I over L2 times S2. Okay? So I need to calculate this one and put it here. You can see I have written this formula here, which represents exactly this one. Let's go through it to see what does it mean. B8 means, see, B8 means E. This B8 is this E. Divided by B11, this B11. Where is this B11? B11 is this one, L. So it's L. Multiplied by bracket B9. B9 is A. This is A. Multiplied by B12 squared. B12 is C. C squared. Plus 12 multiplied by B10. B10 is I. It's here. Multiplied by B13. B13 is S squared. The squared is here. Divided by B11 squared. B11 is L. L squared. So this formula represents exactly this in terms of when we have the 6 parameters here. All right. I have done this for all of these lines, these cells, these cells, and this cell. And when you have this line calculated, you can say this column is exactly like this line because you have symmetricity in your stiffness matrix. As you can see here, it's symmetry. It means that when you have this calculated, this is equal to this. See, this is equal to this. You need to make a mirror for your matrix in terms of in terms of both triangles at the top and bottom of your diagonal line of your matrix. This is the diagonal line of your matrix, and at the top and at the bottom, it's a mirror. So this is equal to this. This is equal to this. This is equal to this. This is equal to this, and this is equal to this. It means that the line 1 is identical to column 1. The line 2 is identical to column 2. The line 3 is identical to column 3. The line 4 is identical to column 4. The line 5 is identical to column 5. And the line 6 doesn't matter because it's already filled with numbers. All right? So it means that you need to, I counted these, you need to write the formulas for 21 cases. These are altogether 21 cases. Although your stiffness matrix is 6 by 6, it means 36 elements are there. However, you need to write 21 cases, and the other cases can be just simply set based on the symmetricity. So if you do this based on this formula, you will get the stiffness matrix for element number 1. All right. And for element number 1, you have the stiffness matrix, which is a 6 by 6 stiffness matrix. All right. Before I go to the next sheet, is there any question? If there is, just feel free to step in the podium and ask me questions. I can hear some steps. All right. When you have the beautiful of Excel is when you assemble this K1, you can make a copy of it like this. Make a copy of it and create a copy. Okay. I will just move it here. This is K12. You can rename it to whatever you want. Okay. And this is a new sheet, exactly like K1. And you can just change whatever you want. Okay. For example, if I, in this new sheet, which I just copied from K1, if I go here and I say, for example, the modular of elasticity is coming from info D2. Info D2 is here. But if I change it to D3, it will be for the next element, for element number 2. Right? I just hear say E is coming from info, but D3. A is coming from info, not E2, E3. I is coming from F2, not F3. L is coming from G2, no G2, G3. C coming from L2, please come and get it from L3. And S, please not from M2, M3. And if you do this update here, these data are coming from info, but from this line. It means that we have these 4 and these 2 parameters fed into this part of this new sheet, and this calculated stiffness matrix is basically for element number 2, not number 1. So it means that you can simply calculate the stiffness matrix for whatever number of other elements you have in your structures. This makes your life very easier. For example, for your coursework, if you assemble the stiffness matrix in one sheet, and okay, you have, I don't remember, you have 9, 10, 8 elements, you can just make a copy of K1 for K2 and just update the input parameters. You can then again copy it for element number 3, 4, 5, 6, 7, 8, and you only write once the formulas like me, and you just use it for different elements very conveniently, very easily, very straightforward. And that's the point of using Excel here. So as you can imagine, I have already done this, and this sheet is exactly like this one. This is K2. I just forgot to put it 2 here. This is K2. And this is just a copy of K1, but with the new parameters from the second element, element number 2. So I just delete this sheet here, and I assume you know how I have done it. I have K1 and K2 for elements number 1 and element number 2, but K2 is simply created based on K1, And for the K1, I had to write formulas for once, and I can use it for as many as times I want based on the number of elements I have in the problem. So is there any questions so far? So when we have K1 and K2 for both elements number 1 and 2, we need to put them together to come up with the big matrix, right? We have the big matrix 9 by 9, it should be, right? Because we have 3 degrees of freedom in each node. We have 3 nodes all together, so 3 times 3 will be 9. The big matrix should be a sort of 9 by 9 stiffness matrix, and this is the K total. I just created an empty matrix 9 by 9, and you can see D1 X D1Y Phi1. This is for element number 1. Sorry, but for node number 1. These 3 are for node number 2, D2X D2Y Phi2. And these 3 are for node number 3, D3X D3Y D Phi3. If you had 5 nodes, you should just continue D4X D4Y Phi4, D5X D51 D5Y P5. All right. Whatever number of elements you have, you need to go on until the end node. I have 3 nodes. I started with 1, 2, 3. I just copied these 9 hints here. I can maybe use the same colors. This is blue, and this is red. All right. So the same pattern here is just coming here. All right. We have a 9 by 9 stiffness matrix, empty. However, when you look at K1, K1 element number 1 was the element connecting node number 1 to node number 2. That's why the K1 should sit here in the gray area, because it's from number 1 and number 2. Number 1 and number 2. The gray area is the area that your K1 should sit there. And the orange area here is the area that the K2 should sit there, because K2 for element number 2 is coming from the element that connects node 2 to 3, right? We decided at the beginning of this problem that the element number 2 is an element which connects node 2 to 3, all right? So the orange one, the K2 should sit here. As you can see, there are 4 cells at the middle here that receive numbers from both K1 and K2. So as we said before, just put those numbers with their actual sign there, and whatever signs they have, they will add together to come up with any sort of number you have. All right. This is a schematical this illustration of the whole stiffness matrix, and we will go through the actual numbers in the next sheet. All right. Is there any question so far in this one? I can see that the colors on your screen probably is a little bit different from my color on my screen. It's because of the video projection setting is different from my computer setting. So Probably when I say orange, you will see some sort of yellow or amber. It doesn't matter. I just wanted to show the different parts of the matrix in different colors. That's the point. Otherwise, just consider that the colors on my screen is different from yours. So I just created this K total, and this is the K total in terms of numbers. So I just copied this one, these numbers into here, and the other numbers into here. But for these, sorry, there are, this part has 9 elements, not 4 elements. Sorry, probably I said 4 elements. This part, which brings the numbers from both stiffness matrices, has 3 by 3, 9. Yeah, 9 elements. Uh, okay. So this part, you need to do it manually. For example, for this one, see, I'm putting one number here plus one number here. All right. It's coming from spreadsheet K1, E4, and a spreadsheet K2, B1. All right. A spreadsheet K1, E4 is this one. E4, this one. A spreadsheet K1, E4 is this one, this number. And a spreadsheet K2B1, K2B1 is this one. So this is gonna add to this one, and they both sit together here. So you need to do it manually in this region, okay? You need to do it manually based on what number from K1, what number from K2 come together, add together, and sit here, all right? So you should just be careful about this area. So the gray area coming from K1, the orange area coming from K2, and the middle one, which is green for me, is coming from both of them. So you need to be very cautious to not to do any mistake here. And this area is 0, and this area is 3, 0, empty. All right. So we have a 9 by 9 matrix here, don't we? Any question on this spreadsheet? If you have any question, just feel free to walk to the podium computer, close to the microphone, and ask your question. Next step is the boundary condition, isn't it? Although we have a 9 by 9 stiffness matrix, but we need to eliminate those rows and columns corresponding to different support we have in this structure. So as you can see from the problem we have 2 fixed support at node 1 and 3. All right. So the 3 degrees of freedoms, delta x, delta y, and theta in node number 1 and node number 3, they are all 0. All displacements in 1 and 3 are 0. 3 in 1, 3 in 3 in 3. 3 degrees of freedoms in 1 and other 3 degrees of freedoms in 3. So it means that these are 0. and these are 0. These are 0, and these are 0. All right. Delta 1 is 0 in terms of delta 1 x, y, and theta 1. Delta 3 is 0 in terms of delta 3x, delta 3y, and theta 3. So because we have the support in node number 1, you need to eliminate these 3 columns. These should be eliminated. And these three rows. All right. I just eliminated the first because of node number 3. And these 3 columns, which means from the 9 by 9 means columns 7, 8, 9 and rows 7, 8, 9. Right? We have eliminated 3 columns and rows because of support in node number 1, and 3 other rows and columns because of the support at node number 3. So 6 rows and columns are eliminated, and only 3 rows and columns are left in the big matrix, which they are corresponding to d2xy theta 2 or phi 2. All right. So the middle part should get out of this, and these are the deformation corresponding to this remaining part for the structure, which makes sense because delta 2x, delta 2y, and theta 1 or phi 1, the rotation, these are unknowns. They are degrees of freedoms which they are free to move. They can have deformations at node number 2. So whatever uh, external force you have can make some sort of deformation. And of course, the deformation depends on the nature of the external force you have on your structure. So the deformations at node number 1 and 3 are 0, but in node number 2, they are free to move. So that's why we see here this part of the matrix remains, which relates the d2xy phi 2 to the external forces, right? So we need to take this out of this big matrix and solve it. So it means that this 3 by 3 matrix multiplied by these 3 unknown vector will be equal to the 3 by 1 vector representing the external forces, which will be F2x, F2y, and M2. All right. I will take these to this new sheet solve to proceed with the problem. But before that, if there is any question, just brings it up. Also, we are in the halfway of the class. Maybe you will need some break, and because it is a good place to pause the lecture, because from this point we want to go to this to solve the problem. Okay, this is the solve the problem, and let's have a short break and come back at 10 past. Okay, 10 past 10. All right, see you in a bit. I forgot to mention, if anybody has any question, just feel free to go to the podium computer and ask me.
Hi, Ali. Can I ask you a question?
Yeah, sure, Bo. How are you?
Yeah, good. So you've stated to use concrete, which I'm presuming if we were to use a reinforced concrete section. So ETABS naturally will, will want to make my my beam a taller section than say a square section that I could use for the column. And so I'll have different values for A in as my scalar, if you like, and then obviously that's different values for L. So would I just because the steel in each section will vary as well, will I just use the value for E? Would it be sensible just to use that from what ETABS generates, or would you recommend that I just make my own value up? So could I try to make this a bit more realistic and use ETABS' values? So if I were to define the section property.
Wait there. Can you see my ETABS on the screen?
Yeah.
If you go to define section property, frame section, all right, you have different choices. However, for example, I will go with adding a new property and concrete rectangular like this one.
Yeah.
So, for example, if let's just wait. Okay. If I just use like depth is 300 millimeter and height is 600 millimeter. Okay. Oh, sorry, it's vice versa. 600 millimeter, 300 millimeter. Okay. For example, you want to assume something like this, whatever you want to assume. Okay.
Yeah.
The material is here. You define the material based on the modulus of elasticity is inside this material. The geometry is here. If you press OK, and if you whole section, it's a name, all right?
Yeah.
If I press OK, it's your own section. If I modify it, just to see again what I have, this is section I have 300 by 600 millimeter. The ETABS automatically calculates the section area and also the second moment of inertia. Like I can see them here, see section properties. The section area is 1800. It should be, isn't it? Because it was 300 by 600.
Yeah.
And the modular of elasticity is this one. If you calculate 1 divided by 12 times 300 times 600 cubic, it's 1 over 12 BH3. Do you remember the formula? The second moment of inertia.
On 12.
Yeah. If you calculate that manually, it's this one. The second moment of inertia for a rectangular section is 1 over 12 times BH cubic.
Yeah, but is that always the same whether it's a composite material like
reinforced concrete, you mean?
Yeah.
Yeah, of course, the true answer to your question is no, it's not. But we assume like that because we don't take the reinforcement effect into the calculation of the second moment of inertia.
Right. Okay.
This is advised by all the codes. Otherwise, if you want to do that, that's very complicated. That's really complicated. Makes the design problem very complicated. We use the second moment of inertia for the concrete section without considering the reinforcement into the problem, and it's just simply 1 over 12 bh3.
Yeah. Okay. So I
And
think I'm getting confused then. Yeah. Okay.
so the modular of elasticity is inside this one, which you define here. If you go, you have two things to work with. It's like the examples I've gone through for the truss structure for the IT labs in general.
Yeah.
Okay, we just went to the material property and created the material. This is my modular of elasticity, 330 gigapascal, 330 gigapascal in this case. It
Yeah.
can be 300 or 250 or whatever, 400. My case is a concrete 3037. This is the grade of my concrete. So because it's like actually it's wrong. Why it's like this? It's wrong. It should be 300, not 330. So it should be 300 uh, 30 gigapascal or 30,000 megapascal. So this is the material. This is the name of the material, and this is the module of elasticity. So this is the place that you put your module of elasticity. And when you have your material, the second part we go is in the section property, which is frame section. And here, when you define your specific section, like pole section, and here you choose your material. When you choose this material, it means that that module of elasticity will be fit here.
Yeah.
Okay, and this is the geometry of your section. So the module of elasticity is really comes from the material type, which is here, and the section area and the second moment of inertia, they come from the geometry, from this geometry. That's why if you change these, the section area and other things will be changed. How does it make sense?
Yeah. No, that's great. I just was getting a bit wrapped around the axle, getting confused with it being there being steel in the concrete and how that
Aha,
works.
aha. Okay, that's
Yeah.
a really good question, but your point is 100% true. When we have a steel into the material, it affects the properties, including the section area as well as the second moment of inertia. However, we just simply neglect it, and the Eurocode allows us to do so because it's a very important simplification. Otherwise, we cannot go forward. It's a very Otherwise, if you don't want to take this simplification, it will be very complicated to proceed with the procedure.
Right. Okay. Nice one. Thank you.
You're welcome. Shall we continue, guys? Good. Before I proceed, I want to mention that there was a question from one of you last week, 2 weeks ago, about if Excel can do matrix multiplication or not. The answer is yes. And today I'm going to use that multiplication possibility in Excel to see how we can deal with different problems just with Excel. We can inverse matrices, we can multiply them together, and that's a big tool to solve any finite element problem, including your coursework. So when we come to this point, we only need this part of the matrix, not the rest for now, to solve the problem and calculate these unknown deformations. All right. For that purpose, this sheet is exactly what I've done in the previous one. We just proceed to this sheet named solve. So this is the matrix coming from the previous one. This part of the matrix, I just copied that part here. So this 3 by 3 matrix should be multiplied by these three unknown deformation, should be equal to this vector of external forces. And these are known numbers, that always the external forces are known. The first one should be F2x, F2y, and M2, just as a hint. Okay, F2x is 0 because F2x means the external force at node number 2 in x direction. Obviously, it's 0. F2y, you can see at node number 2, we have 20 kilonewton upward down. So in this direction, it means that it should be minus 20,000 Newton, because I'm working with the SI system. I just instead of 20 kilonewton, I'm saying 20,000 Newton, and it's minus because it's downside. It's from top to bottom. So it's against the y-axis. The y-axis is like this. So if you remember again, x and y, the coordination system convention was like this at the beginning of the problem we talked about. So M2 is 0 because we don't have any external moment at node number 2. If you had any external moment at node number 2, it would go here. And for reference, if you have any, because for this x and y, the z axis will be, if you just try with your hand and thumb from x to y, the z comes from your plane out. So it means that the positive z is counterclockwise. So it means that if your external moment at node number 2 would be counterclockwise, you need to put the number here without any change. And if it's clockwise, you should put negative of that number. All right? Because the z-axis is counterclockwise. However, here we don't have any M2. So we need to solve this sort of 3 by 3 equation. And here we need to inverse this matrix and multiply the resultant of the inverse by this matrix to come up with this unknowns. All right. The inverse matrix is this one, but I want to show you how we can inverse this matrix first. Uh, I just delete here. You have a 3 by 3 matrix here, all right? And listen here carefully, because this is a very simple but important part of the solution, because you simply can inverse and multiply whatever you want by only e-tabs. You don't need any other things to do so. This is a 3 by 3 matrix that I want to inverse. And you know, for any sort of matrix, the inverse size will be the same as the original matrix. So if it's a 3 by 3, the inverse matrix will be 3 by 3, obviously. So I just select a 3 by 3 space, empty space here, wherever you like. I mean, wherever you like. You can get it here, you can get it like here, okay? Wherever you like, just grab and select 3 by 3 matrix. My mouse is here, okay? I've just selected here. Don't click any other place. If you click, it's been unselected. Just select 3 by 3 and bring your mouse here. Click in this part which you can write formulas, okay? And write like I do, equal, okay, equal M inverse, bracket opens. When you are typing, you can see that Excel tries to help you by providing this part here, which means that it's providing some hint to you how to behave. For example, when I'm writing M, it brings me a list of all comments which start with M. So if you want, you can navigate. Okay, which one was it? Oh, it's this one, M inverse. M. You can have different other commands as well. But if you have forgotten what it was used before, you can find them here. And usually the operators for the matrix start with M. So it's M inverse, not simply inverse. So it's M inverse and start, open the bracket. It tells you that you need to uh, select an array or matrix. Okay. When I'm here, I just go and select these three. Don't click any other places, okay? And you can see it's B2 to D4, B2 to D4. It's blinking here, okay? Again, go back here to the formula, close your bracket. You're done with the formula. It's a tricky point here. Don't click anywhere else. Hold your shift key and control key and press enter. And if you do so, this part will be filled with the inverse of this matrix. Do you want me to do it again? Huh? Was it clear or not? Somebody please tell me. Yes means it was clear, or it's good to repeat it again.
It was clear.
Okay, good. So this is the inverse of this matrix, okay? What I have here. This is the inverse of this matrix. You can make different colors if you want, just to remind what you have. And I want this inverse of the matrix being multiplied by this vector. Okay, how can I do this? Uh, again, you can imagine this is a 3 by 3 matrix, and when you want to multiply a 3 by 3 matrix by a 3 by 1 vector, the result will be 3 by 1 vector, right? Because the result is should be 3 by 3 by 1 array vector, I just selected 3 by 1 like here, an empty space, and I go to the formula and I say equal to M, which means matrix, mult, open the bracket. The Excel tells me M mult, which stands for matrix multiplication. You need array 1 and array 2. So I just go and select my array 1, okay, and go here. Between these two arrays should be a comma, okay? I just type a comma here. And what is the array 2? The array 2 is this one. And I go here and close my bracket. When you close your bracket, you need to hold your control and shift key down and press enter. And with this, you will have a 3 by 1 result here filled by the multiplication of this matrix by this vector. The result is here. Is it clear, or you want me to repeat it again?
Yeah.
Okay, good. Also, we are on record, and I will upload this record as well, so you can repeat it. Let me just check on in the chat if uh, Jamie, do you have any question? It was for before break. Just to confirm, is this process the Euler or Timoshenko? You mean the Excel process? The Excel process is Euler because this is a good question. Because when I started the problem, if you remember today, I used this formula, which is Euler formula. It doesn't have any sort of shear modulus into the problem. It doesn't have any G. Do you remember? The Timoshenko problem has G into it, but this is only the Euler formula. But don't worry about Timoshenko. Timoshenko formula is a little bit bigger, but although it's a bigger formula, but if you put that into the Excel, you can just copy and paste for different elements, and that's not very difficult to do so. So this is the result of the inverse of the matrix multiplied by this vector, which means that we have these. I can put them here. D2x is 0, D2y is this one, and phi2 is 0. To be honest, you could imagine that D2x is 0 because for this structure, the external force is only vertical and the structure is symmetric. So if you remember from undergraduate structural analysis module, when you have some symmetric structure and your external force is symmetric, you don't have any horizontal deformation like the delta 2x. So I could predict this delta 2x equal to 0, but I didn't want to use any sort of this information into my problem because I need to proceed with a universal approach for solution because you might have some sort of external force into the x direction on node 2, or even a sort of external moment at node number 2. So the structure will not be, the structure is still symmetric, but the external forces wouldn't be symmetric, and you will have some non-zero elements, non-zero solutions for delta 2x or phi 2. However, when you come up with this stage, because everything is linked together, all right, you can change these. For example, if I change this bit by 10,000, you can see the solution is already there. 10,000 means I'm assuming I have 10 kilonewton external force in the horizontal direction on node 2. All right. If I fill this here by 15,000 kilonewton meter, Newton meter, actually, counterclockwise, you will see these are again changed. If I decide to change any sort of input properties, the final solution will be changed based on my new input to the problem. This is the beauty of using Excel here, because everything is connected together and you can study the different behavior of your structure based on the different sort of external forces. If you want to repeat this on a piece of paper for a couple of times, it's really a big hassle to do so, because you need to do many different stuffs to repeat a problem if any sort of small changes occurs into your structure. So before I proceed with the other parts of this Excel, if there is any question. Uh, Also, I want to mention that for this example, you have the etabs files here on your Moodle. If you download them, there are 3 etabs files here. If you download them and open them into the etabs, you will see that I've already modeled this structure, the same structure I'm talking about today in etabs. This is a frame structure. These two are supports, and this is just uh, the free nodes. Just take a few seconds to run it. There are pretty good agreement between what we have done in Excel and what we have done in etabs. So first of all, see, we have 20 kilonewton vertically applied on node number 2 here. And if I show the deformation based on this load, you can see the deformation is pretty symmetric. I can exaggerate the deformation here by increasing this scale factor. This is just the scale factor. I'm just exaggerating the deformation. Maybe I'm too much exaggerating. 3. This is the deformation. All right. This is just the schematically shown the deformation. All right. And the deformation values are shown here. This is UZ here because X and the coordination system in etabs here is different from what we have done manually in Excel. In Excel, it was X and Y. Here is X and Z. So Z here is something like Y in the Excel sheet, isn't it? So the UZ, as you see, the UZ is 0.0337 millimeter. And if you go to the Excel, sorry, I need to put this 0 again and this 0 again. And you can see this is in terms of meter. So if you multiply this by 1,000, you will exactly get 0.0, 0.0 37. Was it the same one here? Yeah. This is exactly the value that you're seeing in ETABS as well. So it means that we have some sort of validation for our model that this one with ETABS they are doing pretty similar. However, we all know that the ETABS is using Timoshenko theory, and the Excel that we are talking about is using Euler theory. However, in this case, because we don't have a deep beam sort of kind of element, it's the Euler and Timoshenko are very close together, but it's not the case in your coursework, especially for that short beam you have. So if you go through the Euler theory and Timoshenko theory, you will see some results, especially when you have a deep beam, which means that the height of your section is significant when compared to the length of your element, your beam. That's something to be studied in your coursework, and keep in your mind that ETABS always provides you with a Timoshenko theory, which is the more correct one. So the benchmark to be compared is ETABS. So when you in your coursework, when you solve your coursework based on the Timoshenko, you need to I need and I you anticipate you should anticipate that the results of the Excel and ETABS would be in agreement, but if you do the Euler theory with Excel, it has a significant difference with the not always significant, depends on the student's parameters, but there is a difference between the Euler theory and ETABS when you have a deep beam in your coursework. So how much this difference is, it depends on your specific parameters, and you need to discuss about this difference, and this is one of the aims of your coursework. So any questions so far? When we get to this point, the structure is analyzed, as you know. The unknown deformations are known, but still the other parameters of interest can be found based on these calculated deformations. So when we have these deformations in hand, the other things can be calculated as a function of these. Now they are known deformations. Before this stage, they were unknown. So usually the interest for structure analysis is support reactions or internal forces in different elements. For that reason, I come to the next sheet. Just zoom out a little bit just to be more clear. As you see here, I just brought the 9 by 9 matrix here from K total. Here, we had the K total, if you remember, we eliminated some of them, but now we want all of them. We eliminated just to calculate the unknown deformations, but now we can copy all of these into a new sheet, which is support reaction. And these are all the big matrix. And we just used this part for the calculation of unknown parameter, unknown deflections. But now we have the whole big picture here. And you know, this big matrix multiplied by the deformations, these three deformations are the deformations for node 1. These three deformations are the deformations for node 2, which already calculated. And these three deformations are the deformations for node number 3. As you know, for node number 1, they are 0 because they are support, these three. and these three are 0 because they are support. But these three, we have already calculated them. All right. So these three, which they correspond to these yellow ones, they are the support reactions at node number 1. These three, I see them blue, you too probably. These three, they are external forces at node number 2. We already know them. They are 0, minus 20,000, and 0. And the last set of three numbers here, they are red. They are the support reactions at node 3. All right. We are interested in calculating these three yellow and these three red because they are support reactions at node 1 and node 3. For that purpose, it's very simple. We have this 9 by 9 matrix, the big matrix, and we have the old deformations because we already calculated the unknown deformations, didn't we? So we just need to multiply this by this one. And for example, if you want to be sure, you need to multiply this line by this column, and the result will be this one. And the second line multiplied by this column, the result will be this one. You can do it manually, or you can do it like this. Because this is the 9 by 9 matrix, and this is the 9 by 9 by 1 vector, the result of the multiplication should be 9 by 1 vector. All right? So you can select a 9 by 1 vector and go here, write the formula equal to m mult, start the bracket. The first array is this one, comma. The second array is this one. Close your bracket, hold your shift and control, press enter. And it doesn't work simply, isn't it? Why it didn't work? Uh, D2L10, N2N10.
Do you need zeros in the flow matrix?
Yeah. Thank you. Yeah. Yeah, when it's empty, it doesn't understand it. It's the difference of machine and yeah, thank you. It was Jamie, wasn't it?
Yeah.
Good job, Jamie. Thanks. All right, so these are exactly these ones. All right. So these three are the support reactions for support number 1, and these three are the support reactions for number 3. So it's always the case when you need support reactions, you need to use the big boss, the big stiffness matrix. That's it. And the other interesting parameter you might be interested into is having the element internal forces, like the next sheet. So for element external forces, I need to remind you that for element external forces, you have the 6 by 6 stiffness matrix for each element, and that's enough for calculating what you want for each element. For example, for element number 1, you have this matrix. First I need to where is it? Depends. Depends on what coordination system you want to the internal forces to be calculated. I think so, but let me check which one is this. This is you know what I've done here? I've done the more difficult way of calculating this, but you don't you have two ways to going forward. Let me put them here. Maybe they will be better. Or in a way that everybody sees them. I just used here a sort of local coordination system by using this stiffness matrix. This stiffness matrix is this one. This is this one. And these are the deformations at node 1 and 2, because it's talking about element number 1. And the results will be in local coordination system. All right. But for that purpose, you need to interpret the local coordination system from this convention for your particular element. But it's really the hardest way to go forward. But the easiest way to go forward is to grab the stiffness matrix from this K1. This is the 6 by 6 stiffness matrix, and multiply this stiffness matrix straightforward by the deformations at node 1 and 2, exactly this vector, and this will give you the internal forces at both ends of your element in the global coordination system. And those will be easier to interpret because you know where the global coordination systems are. Otherwise, the global coordination system is one unique, but the local coordination system for element number 1 is different from element number 2. So I recommend to do like that. And let me see if I have any. I think we have it. We have them here. Yeah. If you calculate the internal forces for your elements, you will come up with these numbers in the global coordination system. The red ones, this is Fx, Fy, and M. So these three are the support reaction. Sorry, these are not the element forces. These are the support forces. These are the support forces. We got them from support reactions from here. These are from here. These three numbers go here for these three red, and these three support reactions go here. All right. We have 20 kilonewton here as well. This is a sort of control for your structure because you want to see if you have done correctly or not. And if you write the three equilibrium equations, like the summation of Fx should be 0, and the summation of Fy should be 0, and the summation of M should be 0. For example, the summation of Fx is really 0 because we have two forces, 7,443.9 and the minus exact number here. So the summation of Fx are 0. The summation of Fy, we have 10 kilonewton here, 10 kilonewton here, and 20 kilonewton here. So we have 20 minus 20, 0, right? And if you write the equilibrium equation for the moments, you will have 0 as well, because these two moments are 0, for example, against this point number 1, and this 20 kilonewton will be multiplied by 3 meter, and this 10 kilonewton meter 10 kilonewton meter will be multiplied by 6 meter, and they are zero as well, because one is counterclockwise and one is clockwise. So when you write all the three equilibrium equations, you will see that they are all zero. And just keep in your mind, if you write your equilibrium equation, and for example here, you come up with some sort of numbers like the summation of fx or fy or m is something like a fraction of 1, like 0.5, it's still zero. You can call it zero. It's called a round of numbers error. So when you're working with external forces like 20 kilonewton, which means 20,000 newton, okay, when you come up at the end of the day with the summation of fx equal to zero, no, it is not equal to zero. It is equal to 1 newton, for example. 1 newton compared to the 20,000 kilonewton, it's practically zero. From engineering point of view, it's zero. So, but if you come up with some sort of numbers like 500 compared to 20,000, it's not zero. You have done some error in your calculation, certainly. So if you go to the E tabs, you can also compare the internal forces for different elements, like the moment, or for example, this is the variation of moment and shear in your element, number 1. This is the moment. You can see the moment. The maximum moment is this one. The maximum is shear, this one. This is kilonewton and this is kilonewton meter. You can compare them to whatever you have calculated based on your Excel manual calculation, and they need to be matched as well. So you can go to display you can go and display support reactions as well. See, it is the support reactions, and in this case I need fx, fz, and my, because I'm working in x and z coordination system. So I need these three to be compatible with what I'm working with. And if I take a look at them, that the numbers are very small, but if you go on top of it and leave your mouse, you will see the numbers there. You have fx and you have my. So these are the exact numbers or almost the same numbers we got in our Excel calculation. So the same in the right hand side support as well. So you can verify your calculation based on a simulation, finite element simulation in ETABS, and this is what you need to do in your coursework for that particular example. So I assume that I've reached to the end of my discussion today. I will stay here to have any discussion with anybody who has a question. Just step forward to the podium computer and we can talk through it. Otherwise, thank you for today, and the class is dismissed. If you have any question, just step forward.
Ali, could you quickly go over again the internal reactions? What are those two matrices that are multiplied together?
Yep. See, I need to raise this one first. Can you see this one?
Yep.
This is the stiffness matrix in the global coordination system, okay? And this is the stiffness matrix in the local coordination system, all right? This one correlates the deformation to the forces in the local coordination system, as you see here. Okay. But we have used this for all the calculation for in the global coordination system. Okay. But when you come up with the elements, okay, you can calculate the element. For example, these three forces can be expressed in the local coordination system or in the global coordination system. All right. But I admit that it's a little bit confusing, and let me calculate both ways and record a short video and send it to everyone shortly. All right.
Okay.
Because
Yeah,
but the point is you can use this one for the global coordination system calculation, or this one for the local coordination system, and both should represent the internal forces for each element, but in two different coordination system.
Yeah.
All right. um, I will talk it through. It's a good question. Let me more elaborate it for you in a different video, and I will send an email to everyone about it. Okay.
yeah, that's fine. That's perfect. Thank you.
Thank you. Thank you for your question. Any other question, guys?
No, I think that might be it, Ali.
All right. I think Dr. Reginald is there, isn't he?
It is, yeah.
Okay. He probably needs to log out the computer.
Yeah.
Reginald, I don't see you. Thank you.
Yeah, hi Ali, I'm here.
Thank you.
All right. Yeah, thank you very much. Have a good day.
Indeed appreciated. You feel free to log out.
Okay, thank you. Bye for
Thank
now.
you. See you later.
Okay, see you. Bye bye.